Welcome to the lecture series on condensed matter physics. In the last lecture, we were discussing the classical free electron theory, and in this lecture, which is titled as quantum free electron theory, we will have the following as the contents: the particle in a box, boundary conditions, quantization of energy values, density of states, Fermi-Dirac distribution function, Fermi energy and Fermi momentum. We go through the quantum free electron theory. In the earlier classical free electron theory, we identified the electrons as equivalent to gas molecules, and the molecules, as you know, in a gas can travel with all possible velocities, all possible energies. But in the case of quantum free electron theory, what we do is we make use of the quantum ideas, and the energy eigenvalues of the electrons will be quantized. That means, they will be discrete. The allowed energy values are realized in terms of set of energy values. The distribution of electrons in the various allowed energy levels occur as per Pauli's exclusion principle. The Pauli principle does not come into play in the case of the classical free electron theory, as all of us would have understood. Then we now pass on to particle in a potential box. What is meant by a particle in a potential box? Now, supposing you consider this as a metal, the electrons are there. We are discussing about the free electrons present in a metal, and these free electrons, according to classical physics, can have any energy value. All possible energy values are allowed according to classical free electron theory, but according to quantum free electron theory, as I told you just now, the energy values are quantized. The electrons can have only discrete energy values. You know, even in atom, we take the case of lithium atom, where the number of electrons will be 3, and we write the electronic configuration as 1s2, 2s1. So, 1s2 refers to a particular energy, and 2s1 refers to a different energy. So, the energy values are quantized for electrons and atoms, and similarly in solids also, in a metal the electron energy values should be quantized. So, a particle in a box refers to any bound state. What do you mean by bound state? Electron in an atom will not come out of its own, right. Electron in a molecule also will not come out of its own, and similarly if you take the metallic solid that you have here, the electron cannot come out of its own. So, it is bound. So, any bound state problem is called a particle in a box. What is meant by box? It is experiencing an attractive potential energy, and the electron is bound. Even a nucleon is bound to a nucleus, where in the case of nucleons the energy is the nuclear energy, right. Now, let us apply the Schrodinger equation, because you are in the quantum regime, you are talking about a quantum free electron theory. Obviously, the Schrodinger equation will come into the picture. We have to, what is the objective? We have to determine the energy eigenvalues. We did not talk about the energies in the case of the classical free electron theory. We ended with the expression for electrical conductivity sigma, that is equal to Ne mu, Ne times mu, the mobility, right. That is what we had in the last lecture, but in today's lecture we will obtain the discrete energy values and the corresponding eigen functions or the wave functions. That is the objective of today's lecture. We consider the electron or the particle in general to be in a potential energy box, and the potential energy is assumed to be 0 for the or constant for the sake of convenience between 0 and L. L is the length of the box. So, within the box the electron can move freely, and what will happen to the energy of the electron at x equal to 0 and L? The potential energy will go to infinity, right. The particle in a infinite potential box, right, the infinite potential box. That means, at the end points the energy goes to the potential energy goes to infinity. That means, the particle in question, right, can never escape. We ask the question, what are the values of psi f x or the wave function at the end points? At the end points, x equal to 0 means one of the end points. At that point, the potential energy goes to infinity. If the potential energy goes to infinity, the total energy will go to infinity. Therefore, what do you understand by the question, what are the values of psi f x at the end points? At the end points, the energy according to what you have here, because the potential energy goes to infinity, the total energy will go to infinity, which is unrealistic. Therefore, the wave function should die. The wave function at the end point should be 0. The important, they are the boundary conditions. At x equal to 0, the wave function psi f x should be 0, and at x equal to L also the wave function should be 0. If it is non-zero, what will happen? The particle, the electron will have infinite energy, because the potential energy infinity plus something kinetic energy, whatever be the kinetic energy, total energy will become infinity. In no system can have infinite energy. Therefore, the wave function at the end points should necessarily become equal to 0. Therefore, very important boundary conditions. The boundary conditions are important in quantum mechanics in all the problems, right. So, in the region from x equal to ranging from 0 to L, V is assumed to be 0 for a free particle. The one dimensional Schrodinger equation becomes d square psi by dx square plus 2 m by h bar square into E minus V into psi is equal to 0, but V is 0, and so that becomes 2 m bar square into E into psi. And this 2 m by h bar square can be made as equal to the following. E will be the kinetic energy half m v square, potential energy is 0, right. So, that will be m square v square by 2 m. You multiply and divide by m, and you know the momentum will be p. So, the numerator becomes p square by 2 m, and p is h bar k. What is p is h bar k? It is nothing but the de Broglie relation. Now, therefore, if you look at the equation, if you look at the extreme left hand side E, and you have got h bar square k square by 2 m, and coupling these two, that will become 2 m e by, you take 2 m here, 2 m e by h bar square will be equal to k square. This is an important equation, or E is equal to h bar square k square by 2 m. That will lead to what is called a free electron parabola, right. That is a possible energy values for that the electron can have in a potential box. Is that right? So, the potential energy will become, you have got E is equal to h bar square k square by 2 m, right. This is a very, very important relation, right. This gives you what? The energy that the electron can have will be given by h bar square k square by 2 m, and h bar is h is the Planck's constant, m is the mass of the electron. These things cannot be changed, and so E depends upon k. What is k? K is 2 pi by lambda. So, k is the wave vector. So, unlike the energy of the electron in the case of atoms, where n is a good quantum number, n is no longer a good quantum number when you try to explain the energy of the electron in metals or semiconductors. N should be replaced by k. So, this expression that you have got here gives rise to what is called the very well known or famous Sommerfeld's free electron parabola. This is a very fundamental thing that one should know. You should have studied even in lower class. This is Sommerfeld's free electron parabola, right. So, the energy of the electron can be given only in terms of k. You have got k here. For if you assign a k value, what is the energy, right. Then if you assign some other k value, what is the energy, right. These energies will be discrete, right. The dots, the lines that you can draw the lines. Now, these are the discrete energies, and similarly the momentum also will be discrete, right. K will have discrete values corresponding to the energy values, and the kf is called the Fermi, the uppermost momentum, the highest momentum is the Fermi momentum, and along the y axis the highest energy state is the so called Fermi energy, right. These are the things one should know. So, again going back to the Schrodinger equation d square psi by dx square plus k square psi is equal to 0. The solution of this equation or psi will be a sin a second order differential equation. So, a sin k x plus b cos k x. So, psi will be equal to a sin k x plus b cos k x, which contains the most of the electron both directions. The boundary conditions require, as I told you earlier, at the end points when x equal to 0 and similarly when x equal to L, the wave function should die. I told you the reason also. Now, when you put x equal to 0 at the initial end point, now what happens, psi becomes equal to b, where b is a non vanishing constant, psi cannot be b. Now, therefore, in order that psi becomes equal to 0, b should be equal to 0. That means, your psi should be a sin k x, right, and a sin k x also should be equal to 0, right. Therefore, you write here sin k L at the end point x equal to L, the other point, you go to your sin k L should be equal to 0, otherwise k L should be equal to n pi. Obviously, when if your sin k L should be equal to 0, k L should be integral multiple of pi, right, and which shows that k square L square will be equal to this value, that is your k square is equal to n square pi square by okay, this is what you have here. K square is 2 m e by h bar square, and 2 m e by h bar square will be equal to n square pi square by L square, right. Okay. I am going to get the energy eigenvalues in terms of the n is an integer, right, n is a number, right, it should be a positive integer, positive number, right. That is a very important thing. The energy eigenvalues are the energy levels that the electron will have when the electron is found in a metal according to the quantum free electron theory. The energy eigenvalues are given by an expression of this kind, n square h bar square pi square by 2 m L square. This is a very, very important equation, because I am going to generalize it to 3 dimensions, because your solid materials are 3 dimensional materials, 3 dimensional boxes. Therefore, from 1 dimensional box I will go to a 3 dimensional box, that is the realistic materials, right. Therefore, the energy eigenvalues that electrons can have in a solid, for that I have to generalize, right. I have to go along the x, y, z directions instead of the 1 dimensional potential box which have been considered. The important point is, when you write the energy eigenvalues now, you find the Planck's constant in the numerator pi square by mass of the electron, length of the box, n is the only variable, right. So, n is an integer. So, automatically, because of the introduction of boundary conditions, the energies are quantized. You take the h bar square pi square by 2 m L square as a constant, you can put it as c times n square. C is a constant. So, the energy becomes integral multiple of n square, right. It should be noted that the energy eigenvalues are quantized, or in the other words, they can assume only discrete values. The solution is the eigenvalue, the eigenfunction or the wave function of the electron will be given by, we had a sin k L, right. K will become k L should be equal to n pi. Now, therefore, your wave function will be a sin n pi by L into x. This is the wave function, right. Now, these two quantities that I have blocked are of paramount importance, because we will be generalizing it when you go to 3 dimensions. Now, you find when n is equal to 1, this is your E 1 will be here, n for n equal to 2, your the second eigenvalue will be 4 times E 1, and similarly you go to 9 times E 1, 16 times E 1 and so on, right. The energy values are discrete. Okay, that is the important thing that you come across when you use the quantum free electron theory, right. So, your E 1 is here and E 2 is here, E 3 is here, and eigenstates or the wave functions are plane waves, because you come across the wave function sign, right, a sin k x or a sin k L, that is we wrote. So, your sine function sinusoidal wave function that you have here, these are your psi 1, psi 2 here, psi 3 here, they are the wave functions that the electron will have in a one dimensional box. So, the eigen values are here E 1, E 2, E 3, the eigen functions are psi 1, psi 2, psi 3, and the eigen functions cannot be measured. What can be measured in the laboratory are the square of the wave function, psi 1 square, psi 2 square, psi 3 square, these are the things that can be measured, or E times the psi 1 square, psi 2 square, psi 3 square will give the charge density, things which can be theoretically determined, experimentally plotted using X-ray diffraction or neutron diffraction. Therefore, we focus on psi 1 square, psi 2 square, and etc. That gives the electron density of the particle in a box. So, you are the one dimensional box psi 1 square, psi 2 square, psi 3 square, assume the forms as shown in the diagram, and we now pass on to the 3 dimensional solid, right, because solids are 3 dimensional objects. As I told you earlier, in the one dimensional particle in a box problem, in the one dimension we wrote E is equal to n square h bar square pi square by 2 m l square. I told you earlier n should be replaced by n x, n y, n z along the x, y, z directions for 3 dimensional solid. Therefore, when n x is 1, n y is 1, n z 1, that refers to a well defined quantum state. Similarly, when n x is 2, n y is 1, n z is 1, then that refers to another quantum state. You can assign various positive integral values for n x, n y, n z, they will give rise to discrete eigenvalues, right. So, let us write n x square plus n y square plus n z square is equal to r square. If you write like that, the energy eigenvalue will become r square h bar square by 2 m l square multiplied by pi square. These are the energy eigenvalues, right. So, in this particular expression we have arrived at for obtaining the expression for what is called density of states, right. It is a very important quantity, density of states, important quantity for metals, semiconductors, etc. right. Now, we wrote r square is equal to 2 m l square by pi h bar square into E, and r obviously will be this much, and dr, when you differentiate that your r with respect to energy, you get an expression of this kind, and n x, n y are all positive integers. Only the positive octant of the integral sphere will have to be considered. You have the figure which I will show now. The volume occupied by each of the quantum state will be unity in the integer space, and hence the number of states per unit energy will be given by an expression of this kind. And before I go to that, I will show the diagram, right. You have the integer space. As I told you, your n x, n y, n z will take integral values for and we have had an expression for r, right. We had an assumption r square is equal to r square here, right. N x square plus n y square plus n z square is r square. Therefore, what you will have now is you are working in the r space or integer space or momentum space or energy space, right. Now, why I am telling this is, now every point here in the integer space, you can have this as 1 1 1. You assume the all the directions, n x here, n y is here, and n z is here. Look at the volume space. In the volume space, if you assume this point here, and for this point n x may be 1, n y may be 1, n z may be 1. This refers to a particular momentum state or particular energy state, because the energy and momentum are connected, and you have energy state here, and the question that we ask, what is meant by density of states? The number of states or the number of energy levels that lie between E and E plus d E, that is equivalent to finding what I have shown here, E and E plus d E, that is equivalent to finding the number of points which lie between r and r plus dr. What is dr? Dr is the width of the annular ring. You got a ring here with radius r, and this bigger sphere or bigger circle in 2 dimension is r plus dr, and in this dr, what is dr? Dr is nothing but d. Dr corresponds to d, right. You say the number of energy levels in the range E and E plus dE corresponds to, it is nothing but or corresponds to the points that you have in the integer space between r and r plus dr in the annular ring, right. So, I told you 1 1 1, this may be 2 1 1. Therefore, something like for 1 inch you got a point, another inch you got a point. So, in unit volume, that you take the total volume, in unit volume you will have 1 point, right, another unit volume you will have 1 point. So, you find out the total volume, and in the total volume, the volume that you have got here, per unit volume you have got 1 point. So, if you take the total volume, and that will be the number of points or momentum states. So, the density of states will be given by this particular thing that you have got here. I told you that only in 2 dimensions n x n y will be positive, that will be 1/4 of picture that we will have in 2 dimensions, but in 3 dimensions only 1/8 of the octant will have positive integral values. So, therefore, we write the density of states is 1 by 8 times 4 pi r square dr. This is 1/8 is important. The 1/8 of the total volume alone will have n x, n y, n z, all of them will be positive. What is 4 pi r square dr? That is the volume of the annular ring. I showed you the annular ring, the volume of the annular ring is 4 pi r square dr. In this volume, I am talking about this volume, right. 1 by, this is the 1 by 8, in 2 dimensions it will be 1 by 4, but in 3 dimensions it will be 1 by 8 times 4 pi r square dr is the volume, and for every unit volume you will be having 1 lattice point. Okay. And so, the number of states you will be having between energy E and E plus dE will be given by pi by 4. These things you can read for yourself, 2 m L square by pi square h bar square to the power of 3 by 2 in e to the power of half. That will be equal to volume you have here L square, and okay, the entire thing will become L cube V by, okay. This is what you will be having. So, this by simplifying you will be getting the density of states dE will be the volume of the metal by 2 pi square 2 m by h bar square to the power of 3 by 2 into e to the power of half. The essential point is the density of states will be directly proportional to e to the power of half. Is that right? The density of states, what is the density of states? The number of energy levels between E and E plus dE. Why do you need all these things? Not only in metals, in semiconductors you will come across conduction band, valence band, these things I will come to that later. In the conduction band, how many energy levels are there, and how many energy levels are in the valence band, and whether they are occupied, unoccupied, all these things will come to the picture to find the total number of electrons in the conduction band, total number of holes in the valence band, number of electrons in the conduction band. So, in metals one finds the density of states curve follows a parabolic behavior, as I will show later. Indeed, for simple metals such as sodium, aluminum, etc., the density of electrons follows almost a parabolic behavior, otherwise it will be much more complicated in the case of transition metals. Therefore, this particular expression dFE proportionally to the power of should be by heart, it should be remembered, right. It is what you have now, it is the density of states profile for free electrons, right, and you have the energies here, and the energy values will be discrete. As I told you, when you talk of quantum free electron theory, you have got electrons, and the energy states will be discrete. We have been talking about density of states and so on. So, energy states will be discrete, and what is the uppermost energy level? That is the Fermi energy. The position of Fermi energy and density of states the Fermi level are indicated as they are the relevant parameters for calculating the physical properties of solids. Now, when we go to the lectures to come, we will understand the significance of the Fermi energy and the number of states which are there corresponding Fermi level, right. D within bracket E of f. E of f is here, the density of states profile is here. Okay, that these two are very important parameters, and whether a level given is occupied or unoccupied is given by so called Fermi-Dirac statistics, right. What is f of E? F of E gives the fractional occupation of the electron being found at a particular energy level E, right. I told you that electrons have different energy values, right. In a metal or even in a semiconductor, you have got conduction band, valence band, the energy values will be discrete, right. They will be arranged in a series of energy levels will be there, and you take a particular energy value E and you ask the question whether this energy level is occupied or unoccupied. The occupation probability is given by an expression of this kind f of E, that will be 1 by e to the power of E minus E f by k t plus 1. That is the relation obtained by Fermi and Dirac. This is called the Fermi-Dirac distribution function. The Fermi-Dirac distribution function is defined as f of E is equal to the expression that you have here. This gives the fractional occupation that the electron will have at the energy E. Whether the energy level E is occupied or unoccupied is given by the expression of this kind. You take this energy, right, this energy after E f. Is it occupied or unoccupied? It is occupied. What is occupation probability? It may be 0.1, right. And the important thing is, again, mathematically, if you look at the expression once again, when you put E equal to E f, what will happen? E equal to E f will be 0, E power 0 will be 1. So, 1 plus 1 will be 2 in the denominator, and so f of E will be equal to 1 by 2. When will you have f of E equal to 1 by 2? When E equal to E f. Therefore, you find in the diagram here, when E becomes equal to E f, when E becomes equal to E f, you have here f of E will be equal to half, right. As I told you, mathematically the Fermi-Dirac distribution function will assume a value which is equal to half when E is equal to E f. This is the energy axis. When E is equal to E f at the Fermi level, f of E will be equal to half. Is that right? The variation of the Fermi-Dirac distribution function with temperature is shown here. At T equals 0 Kelvin, the highest energy the electron will have is the Fermi energy. How do you define Fermi energy? Fermi energy is the topmost energy level that the electron can have at absolute 0, and the topmost, the maximum energy that the electron can have in a metal at absolute 0 is the Fermi energy. You can have 100 electrons, free electrons in a metal, and how many states are required? If you have 100 electrons, one discrete energy level, another discrete energy level, number of series of discrete energy levels will be there, and the topmost energy level, the uppermost energy level will be the Fermi energy, right. And to accommodate 100 free electrons, you require 50 energy levels. The 50th energy level is called the Fermi energy. Is that right? This is at 0 Kelvin. Now, at a temperature, any other temperature, there will be tail. The Fermi-Dirac distribution function will not fall abruptly to a value like this, but it will have a tail like this, right, the Boltzmann tail, and mathematically, as I told you, your Fermi-Dirac distribution function will be equal to half. Physically don't ask what is the meaning of that. In particular, we have at T equal to 0, all energy values will be allowed, right, will be at T equal to 0, all energy values will be occupied. F of E will be equal to 1, it is occupied. F of E will be 0 when you cross the Fermi energy, right, at T equal to 0. Okay. And that is the thing that you have with regard to Fermi-Dirac distribution function. Now, let me try to summarize this lecture. The classical free electron theory, which treated the electrons as gas molecules which could not be explained by various properties of materials in solids, which can be explained on the basis of quantum theory. That is what we now try to do, we make use of quantum theory, wherein the quantum particles or the electrons should be treated using quantum mechanics, right, using the Pauli principle. The particle in a box problem gives us the quantized energy levels of electrons in solids, and as I told you earlier, also the density state expression is very important. Along with that, the Fermi energy. These are the two important quantities which will be used to calculate various physical properties of all kinds of materials in the area of condensed matter physics. Thank you.